In this video, I want to go over some important points about dealing with head and groundwater flow in the unsaturated zone or the soil zone. So here's a cross section of the earth, and remember down here below the water table we have the groundwater zone. Pores are saturated with water. Above the water table we have the soil zone where there is air in addition to water in the pores. And one of the basic things to remember is that Darcy's law, which says that groundwater flows from high head to low head, works wherever we're in the subsurface. So it works just as well in the unsaturated soil zone as it does in the saturated groundwater zone. So in order to determine the direction of water flow in either the soil zone or the groundwater zone, we need to determine the head, and then head will flow from high head to low head. So we started by looking at how to determine head in the groundwater zone. Remember how that went. Let's say we pick a point here beneath the water table and we want to determine the head. We insert a piezometer, which is a tube with an opening at the point at which we want to measure the head. And so there's a little opening. It's a bunch of slots. Water is going to enter the piezometer, and in the saturated zone, water is going to enter the piezometer and push up against atmospheric pressure to some elevation. So this is the level of water in that piezometer. And I've drawn this kind of importantly, in this particular case, it's above the water table. Importantly, there is not necessarily any relationship with the water table. The head in the piezometer can push up higher or lower than the water table or equal to the water table. But you don't need to worry about the water table because there is no a priori reason why the head at a point below the water table would have to equal the elevation of the water table. And in this particular case, it doesn't. Then, in order to determine the head at this point right here, right, we're determining the head right there at the point where water enters the piezometer, we first have to define a datum elevation so that the head is defined as the elevation of the water in the piezometer, this level here, above that datum elevation. And further, we could deconstruct the head into its two components, the elevation head, which represents the elevation of the entry port above the datum, which is known as the elevation head. Sometimes we use the symbol H sub Z, and usually just the symbol Z, and the pressure head, which is equal to the elevation of the water in the piezometer, which is known as the pressure head, H sub P, which can be shown to be equal to, it's related to the pressure, right, of the water at that point, is equal to P, the water pressure, the gauge water pressure, divided by rho. That's the density times G. I hope it's clear that the upper one here, this is pressure, and this symbol below is the Greek rho, meaning density. Let me try to clean those up, so that we can write the relationship that the head, the hydraulic head, is equal to the sum of the two components, the elevation head, Z, plus the pressure head, H sub P. I'll just call it H sub P from now. And when the point is below the water table, it's very easy to visualize this. Well, when we're above the water table in the soil zone, things change, but they don't change all that much. The main change above the soil zone here is that now in this region, the gauge pressure P is less than 0. And the consequence of the gauge pressure being less than 0, that doesn't mean the pressure is negative, meaning that it's less than atmospheric pressure, right? But the consequence of that is if I were to put a piezometer in at a point like this in the soil zone, this is what would happen. We would see nothing, and the reason is that the water pressure here is insufficient to push water into the piezometer and up against atmospheric pressure because it's less than atmospheric pressure. In fact, if I were to put water into the piezometer, it would get sucked out of the piezometer and into the ground. So as a result, we can't look at that simple picture we could before and equate the rise in water in the piezometer to a pressure head. We can still have the concept of elevation head. That's completely still valid. The green distance is still the elevation head of this point right here, but we can't obviously and easily see or measure the pressure head because the pressure head is less than 0. However, let me point out that these relationships here still hold. This is still true. that the head is equal to Z plus HP. And it's still also true that the pressure head is equal to P over rho G. It's just that the pressure now here is negative, and as such, it doesn't reveal itself as something that's easily measured. Now, under these conditions, what we do is we sort of redefine what we call the pressure head. So in this area here now, and I'll write it out, let's write it in green to be consistent here. The equation for Darcy's law is still H equals Z plus HP, but we now call HP psi, and we call that the matric potential. Okay, so this thing here is entirely equivalent to HP. It is still HP. We have just given it a different name. It's no longer called the pressure head, it's called the metric potential. And its relationship to pressure is still given by this equation here. So we can write that the metric potential is equal to P over rho G. The only difference here now is that since P is negative, the metric potential psi will always be less than 0. So the head here is equal to Z plus psi. Psi, however, is always going to be less than 0. In the way I like to teach this, everything else remains the same. This is still the hydraulic head. This is still the elevation head here. This is still the hydraulic head. The only difference between the equations below the water table and above the water table is what name we call the pressure head. Below the water table, we call it the pressure head. It's an easily seen and measured variable. It's the elevation of the water. It's the height of the column of water in the piezometer. Above the water table in the soil zone, it's got exactly the same idea. It's got the same dimensions. It's got the same meaning, except now we call it the matric potential, and it represents something that we cannot directly measure because it is less than 0. So it is something that has to be sort of either inferred by measuring the pressure and calculating it. For example, if we had a way to measure that negative pressure, we could calculate the matric potential from this equation here. Now, one other final thing to note is that because the matric potential is always negative, we sometimes find it useful to use a very similar concept, which is called the matric suction. I'm calling matric and matric. I'm using both pronunciations. You'll hear both. Matric suction here, which is the absolute value of the matric potential. The only difference between matric suction and matric potential is that matric suction is always positive. So it removes the forcing us to use a negative number in our calculations. So matric suction is always a positive number. Matric potential is always a negative number. But other than that, these equations are exactly the same ones we used in the saturated zone. The only real difference is what we call the pressure head. Below the water table, we call it the pressure head. Above the water table, we call it the matric potential.